Hey, so welcome back to my channel. So I'm recording this one back to back with the inverse Laplace transform, just because yeah, I have the moment to actually record while my wife is like running outside with the children. She says she's doing watercolors with them, and so we'll see how that goes. They might have an early bath time. Anyways, so what we're going to be doing today is we're going to be using the whole concept of inverse Laplace transforms to solve differential equations. So what we're going to do is we're going to take a linear differential equation with constant coefficients, and we're going to apply the Laplace transform to both sides. Now on the left-hand side, the differential equation ends up getting converted to being a polynomial and times y of s. And on the right-hand side, we're going to have whatever's over there and Laplace transform it. So if x is over there, it becomes x of s. If we just have a function like e to the at, it's going to be 1 over s minus a. Then you solve for y of s, and then use all the partial fraction decomposition on the right-hand side. And then once you do that, you have an expression for y, and y is solved. But y is solved in the Laplace transform domain. So you want to get out of there, and then you apply the inverse Laplace transform to both sides. And that gives you y of t is equal to whatever you get by using inverse Laplace transform term by term with those rational functions that you found using partial fraction decomposition. So, and that's it. That's the whole thing. I just told you the entire section, and if you feel confident in everything I said, turn off the video and I don't know, practice your pencil spinning. So let's see what else I want to talk about today. So before we jump in, I thought I'd talk about a little bit of a mathematician who recently passed away just a couple weeks before the quarantine. This is a mathematician who was in his 90s, and he was still working at the Institute for Advanced Study at Princeton. This mathematician, it was Freeman Dyson. He also would be considered a physicist, but I think to a large part he thinks of himself as a mathematician, or he thought of himself. So I had a brief occasion to meet him, actually. He came to the University of Florida while I was a graduate student there. And initially he was supposed to come to the Ramanujan 125 conference, where he was going to give a talk about some of his work that was related to Ramanujan. It worked on a lot of problems in number theory and the partition function. And these included a lot of generating function type stuff. This is the second time I mentioned generating functions, by the way. We mentioned them briefly, Laplace transforms, etc. You don't have to really know how to use them yet. But yeah, so he was supposed to come to the University of Florida, but this was background when we had Hurricane Sandy going through up the East Coast. And Sandy ended up hitting New Jersey pretty hard, so he couldn't end up coming. I had picked up a book. I don't know if it's on my bookshelf right now. Let's see. Book. Hang on. I'll get the book. There. Anyway, so I'll just put a picture here of the book that he wrote. He wrote several, but this is a particular one I picked up. And my brother's a physicist, and he's a big fan of Freeman Dyson. And I was going to get him to sign the book and give it to my brother as a gift. Later I found out that Freeman Dyson isn't really big on book signings. He really just wants to come for the mathematics, and I absolutely respect that. But yeah, I didn't know that at the time, and so I brought the book and I was going to have him sign it, but then he ended up having to cancel his trip. And so, and since he was, having to deal with all the repercussions of Hurricane Sandy, we we all at the Margin 125, we got a couple cards for him, and we signed them and we sent them up to Freeman Dyson. So rather than Freeman Dyson coming down and signing a book for me, I ended up signing a card for him. So he had my signature up in New Jersey, which I thought was ironic. Later on, he actually came down, and I had an opportunity to meet him in person to the University of Florida. He ended up giving 3 talks. I think he gave one colloquium talk in the math department. I think he gave another talk specific to number theory. Or actually, I think it was Markov chains or something. And then he gave another talk over in the physics department. And so I had an opportunity to meet him and talk to him for a little bit. Although as a little graduate student, I mean, I was starstruck and I couldn't really think of anything else to say. He was a very kind person, and he was very patient with me. But then he had his friends he wanted to go talk to, so I don't blame him. Anyway, yeah, it turns out my brother actually met him independently in between those 2 times. So I mean, my whole idea of like, hey, I met Freeman Dyson first, and here you go. My brother had met him at another conference, so there you go. But yeah, Freeman Dyson, he was really famous for doing something called actually popularizing a method of Richard Feynman, and convincing Oppenheimer that Feynman diagrams were actually the real way that you want to go about quantum electrodynamics. And so, and Oppenheimer was so impressed, I'm pretty sure it was Oppenheimer, I'll have to double check that, that he ended up giving Freeman Dyson a lifelong position at the Institute for Advanced Study. What's interesting there is, just from a sort of bureaucratic academic standpoint, is he doesn't actually have a PhD. He got his bachelor's degree in mathematics, and he went on to he went on to actually a professor position, I think, at Cornell, I believe, where he was actually able to mentor PhD students. This is not something that would ever happen today. If you don't have a PhD, you can't be a professor. And so it's very interesting that he had that. Freeman Dyson, by his own admission, said that he can't really pay attention to problems for longer than, say, 2 years. And so, which isn't really conducive to working with graduate students, because they are usually there for like about 4 or 5 years working on a problem. And so by the time his students resolve an issue, he won't care anymore. So he was happy to go on to the Institute for Advanced Study and take his like full tenure position, where he was just free to do any research he wanted, and then he could just take on postdocs and work with them one at a time for quick 2-year sessions. So yeah. In any case, it's unfortunate that we lost him, but we were really lucky to have him for as long as we did, and yeah. So take care, Freeman Dyson, and we will miss you. Okay, so with that, not to be too somber, let's go on into solving differential equations. All right. Actually, the second time I've recorded this because I got something completely backwards when I was going through these problems, and so if I sound exacerbated or impatient, then that's probably because I'm doing all this a second or a third time. Okay, so what's the whole idea? So if you recall from the Laplace Transform properties section, if we take the nth derivative of f and then we look at its Laplace transform, you can this actually turns into s to the n times the Laplace transform of f, and then we have all these extra terms from its initial value. So we have Sn minus 1 going with no derivative. Then we have Sn minus 2 going with, say, the first derivative, and etc. all the way until we get s to the s to the 0 times f to n minus first derivative at 0. Okay, so that's the idea. Let me double check so I don't screw up anything again. Yeah, that's exactly right. Okay, so that's the whole idea. We found out from the properties section that we exchange differentiation with respect to t for multiplication by s to the n. And this allows us to convert a problem about derivatives in differential equations to a problem in algebra for Laplace transform. So the special case that we're really going to be looking at this for is, say, f prime of t of s, and so that's going to be, say, s times capital F of s for our Laplace transform of f minus f of 0, and then we're also going to be using the second derivative a lot, because most of what we look at are like second order linear differential equations in this section. So you get here s squared times f of s minus s f of 0 minus f prime of 0, right? Okay, so we're going to be using these formulas over and over again throughout this section. So if we take a look at, say, the first example out of this section. This is in Nagel, Saff, and Snyder's book. So what are we going to find? Well, we have, for this example, we're looking at y double prime minus 2y prime plus 5y is equal to minus 8e to the minus t. And this is when we have y of 0 is equal to 2, and we have y prime of 0 is equal to 12. Okay, so I'm going to take a Laplace transform on both sides. So we need to convert y double prime using the formula here. Then we need to convert y prime using this formula here. And y just gets changed to be capital Y. And we remember the Laplace transform of, say, e to the at is equal to 1 over s minus a. Okay, so let's go ahead and do this. So since we know that the Laplace transform is linear, I can do this term by term and add them back together. So in the Laplace domain, we get s squared times big Y minus s times y of 0 minus y prime of 0. Then I have minus 2 times s times y minus y of 0. Then I have plus 5 times y. This is equal to minus 8 times 1 over s minus a. All right, so I'm going to go ahead and factor out s squared minus 2s plus 5 from all these y of s's. Then I'm going to go ahead and insert y of 0 into here. So I get minus 2s, and just stay consistent, let's leave y. Then I get minus 2s, and I get minus 12, then I get minus negative 2 times y of 0, and so that is going to be plus 4. It's equal to minus 8 over s plus 1. So then I get s squared minus 2s plus 5 times big Y is equal to, say we have 2s minus 8, or plus 8, and then we have minus 8 over s plus 1. All right, and now if I add all these together, I get 2s plus 8, and then divided by s plus 1 times s plus 1. Then we have minus 8 over s plus 1. So now let's multiply, FOIL out this top part. So that's going to give me 2s squared plus 8s plus 2s plus 8. And that divided by s plus 1, minus 8 over s plus 1. And now the 8s plus 1 cancels that 8s plus 1. I get 2s squared plus 8s plus 2s. So that's going to be plus 10s divided by s plus 1. All right, good. So that tells me then that y of s, the Laplace transform of y, is going to be equal to 2s squared plus 10s divided by s plus 1 times s squared minus 2s plus 5. Okay, so good news is we've solved our differential equation. It's whatever
transforms into this y of s. So now what we have to do is, in order to get a solution in terms of t, is we need to go ahead and use the inverse Laplace transform on y. In order to do that, we're going to use our table. And when we use our table, in order to use our table, then we need to actually use partial fraction decomposition here first. So let's go ahead and do that. Okay, so all right, so let's see how we do this. So I need to see what sort of denominators I have here. So we have s plus 1, that's good. This one, is that an irreducible? Let's see. So we got s squared minus 2s. I'm going to complete square by adding and subtracting b over 2 squared. So it's going to be plus 1 and minus 1, so that leaves into this. So that gives me s minus 1 squared plus 4. All right, and that indeed is irreducible. So instead of writing this, let's go to small eraser. Instead of writing this, let's go ahead and put it in this other form, s minus 1 squared plus 4. Okay. All right, now let's see what we get. So we get y of s is equal to 2s squared plus 10s divided by s plus 1 times s minus 1 squared plus 4. This is equal to a over s plus 1 plus bs plus c divided by s minus 1 squared plus 4. All right, now we just need to figure out a, b, and c are. So I'm going to multiply both sides by the denominator here. And so then we're going to get 2s squared plus 10s. And that is equal to a times s minus 1 squared plus 4. And then plus bs plus c times s minus 1. So I can quickly figure out what a is just by choosing s is equal to 1. And on the left-hand side, that's going to give me 2 plus 10, so that's going to be 12, is equal to, putting in 1, so I get a times, oops, not 1, sorry, little typo. This should have been plus sign here because of this, right? Okay, so now it's negative 1 I want to go ahead and put in, so I get s is equal to minus 1, and what does that give me? So that gives me 2 minus 10, that gives me negative 8. Now on the right hand side, I'm plugging in negative 1, so I get a times negative 2 squared plus 4, and that's going to give me 8. And then on this other term, it doesn't matter what bs plus c is, because s plus 1 is 0 when you put s equals negative 1. So then that gives me a must be equal to negative 1. All right. Now let's see what else we can find. So there's nothing that will cancel out this term, because that is actually an irreducible. So what I'm going to choose instead is I'm going to choose, say, 0 to at least kill the b. And then I can plug in what I found for a already, and so then that tells me this. So s equals 0 gives, so 0 on the left-hand side is equal to negative 1 here plus 4. It's going to give me 5, plus 0 plus c, and then that's going to give me times 1. So that tells me then that c is equal to 5. All right, now we have one last thing to figure out. There's nothing else we can really pick that's going to make it easier, so why don't we just pick s equals 1. On the left-hand side, with s equal to 1, we get 12. And on the right-hand side, I get minus 4 plus b plus 5 times 2. All right, so then negative 4 combines with 12 to give us 16, divided by 2 gives us 8. So then I get b plus 5 is equal to 8, and that tells me that b itself is equal to 3. Okay, so what does that tell me then? That tells me that this is actually equal to minus 1 over s plus 1 plus 3s plus 5 divided by s minus 1 squared plus 4. Okay, so now we need to actually invert this. So we're almost there. I know if I apply a Laplace transform for this, this should give me e to the minus t and minus sign. But I don't know what I'm going to get out of this other piece, and that's because basically these are Laplace transforms we have. So like I said, we have e to the at is equal to 1 over s minus a. But then we also have Laplace transform of, say, e to the at times sine of bt. And what is that going to give me? Well, that gives me b over s minus 1 squared plus b squared. Then we have the last one here, where it's the Laplace transform of e to the at cosine of bt. And this is going to give me s minus 1 on the top, or not s minus 1, s minus a on the top over s minus a squared plus b squared. So what we're looking here, since we have s minus something squared, and that sum is 1, that means that we're looking at a multiplication by e to the t of sine or cosine, and we have then that a is just 1. So it's going to be e to the t times sine and cosine are going to be terms we get, but then we need to know what they're multiplied by. So let's go ahead and figure out how to actually invert this. So what we're going to do is we're going to take a look at, say, 3s plus 5 divided by s minus 1 squared plus 4. Now what I want is something that's s minus 1 on the top, and then I want something where it's 2 on the top. So let's go ahead and do that. So what I'm going to do is I'm going to take that s, and I'm going to add and subtract 1. It's a mathematician's clever way of adding 0. So nothing actually changes. Now if I distribute the 3 through, so I get 3 times s minus 1, and then I have plus 3, that's going to convert into an 8 over here. And then I get 3 times s minus 1 divided by s minus 1 squared plus 4. And then plus this 8, I'm going to turn to 4, so I have a 2 up here. And then I'm going to be left with s minus 1 squared plus 4. Okay, good. So now when I use the inverse Laplace transform here, so Laplace inverse, that's going to give me 3 times e to the t times cosine of 2t. And this one's going to give me plus 4 e to the t sine of 2t. And now this other bit coming from here, that's going to give me, say, minus e to minus t. And let's clean this up a little bit. So now we have this. We'll put this right in the middle. Oop, this is what we get for y of t. Okay, cool. So this is the solution to the initial value problem. Now what's interesting is that before, what we would have done is we would have had to do the method of undetermined coefficients. So we would have guessed our solution to, for a particular solution, we would have guessed a times e to the negative t. We would have plugged it in here for y, and then we would have figure out what a must be. Then after that, we would determine the homogeneous solutions to this, where we find the roots of the characteristic polynomial, we factor that, and then we would have some free variables that we need to choose, that the C1 and C2, that would be determined by whatever these are. Notice we got to skip all of that just by using partial fraction decomposition. This and this are actually solutions to a homogeneous equation, and this is what we would have gotten out of our guess. The a would have turned out to be -1. So that we didn't have to use the method of undetermined coefficients, and we didn't have to appeal to the characteristic equation. It all just fell out naturally from the Laplace transform. So that's a nice little result. Okay, so now let's talk about another problem. The next example in the section is that wants to solve the initial value problem. Where we take y double prime plus 4y prime minus 5y is equal to t e to the t. And we have these initial values. We have y of 0 is equal to 1, and we have y prime of 0 is equal to 0. Okay, so what do? Well, we take a Laplace transform on both sides. So that's going to give me s squared times big Y minus s at y0 minus y prime of 0 plus 4 times s times big Y minus y of 0. And then we have minus 5 times big Y. Now on the other side, we have Laplace transform of t e to the t. So if you remember, Laplace transform of t is equal to 1 over s squared. So then multiplying by t gives us a shift. So the Laplace transform of e to the t times t is equal to 1 over s minus 1 squared. So I like to memorize as few properties as I can in order to get at what I need to. So I just remember a few things like this, and then I just remember that this gives me shifts. Of course, you will have the table on the exam, but it might save you a little time from looking it up if you remember all these things. So in any case, this should be 1 over s minus 1 squared. All right, now let's plug everything in. So, and also I'm going to factor out big Y. So I get s squared plus 4s, and then minus 5 on big Y. Then I get minus s times y of 0, so it's minus s. Then I get minus y prime of 0, but that's just 0, so we can ignore that. Plus 4 times negative y naught, and so that's going to be negative 4. And then this is equal to 1 over s minus 1 squared. All right, now I'm going to take this term, I'm going to move it over. And so I'm going to have s squared plus 4s minus 5 is equal to, times big Y, is equal to 1 over s minus 1 squared plus s plus 4. Now we find a common denominator, so s minus 1 squared and s minus 1 squared on top. And in order to find that, I actually have to multiply this out, so it's going to be 1 over s minus 1 squared plus s plus 4 times s squared minus 2s plus 1 divided by s minus 1 squared. Still a little bit more work to do. So what do we get? Let's see. So we're going to end up with, say 1 over s minus 1 squared. Let's keep it simple. So we end up with s cubed. I end up with s cubed minus 2s squared plus s. I get plus 4s squared minus 8s plus 4. You know, just use your favorite method of working this out. And now put all this together. This was a cube on it. S squared. There we go. All right, now let's add everything together. So we get s cubed minus 2s squared plus 4s, so it's going to be plus 2s squared. And then minus 8s plus 8, that's minus 7s. And then I have 4 plus 1 plus 5. All of this divided by s minus 1 squared. Now, because I'm lazy, I'm going to copy. And I'm going to paste. And now I'm going to write y of s is equal to this divided by s squared plus 4s minus 5. Okay, so next step is we need to figure out where, if we have irreducibles or if this can be factored. Well, s squared plus 4s minus 5 indeed can be factored, and so we're going to be left with s cubed plus 2s squared minus 7s plus 5. And all of this is divided by s minus 1 squared cubed now, because s squared plus 4s minus 5 factors into s minus 1 and s plus 5. All right, so that's where we are with this. It does not look friendly. Okay, so what do we need to do? I need to break this up, or we need to break this up. We'll work together using partial fraction decompositions. Right, and now let's see what happens when we do that. So I have y of s here is equal to, all right, so partial fraction decomposition, we have a linear repeated root, so we need to have an appearance of each number. So we have s minus 1 to the first power, and b over s minus 1 to the second power, plus c over s minus 1 to the third power, plus ds plus e divided by, oops, not ds plus e, sorry, that wasn't irreducible, it's just s plus 5. Okay, that's what we have. Now I need to figure out a, b, c, and d. All right, well, let's go ahead and multiply both sides by the denominator here. And what is that going to give me? Well, it gives me s cubed plus 2s squared minus 7s plus 5 on the left is equal to a times s minus 1 squared plus b times s minus 1. Sorry, s minus 1 squared times s plus 5 plus b times s minus 1 times s plus 5 plus c times s plus 5 plus d times s minus 1 cubed. All right, there's no real pretty way of solving this. So let's go ahead and talk about how to do it. All right, so if I can go ahead and just choose s is equal to 1, for instance, I do get c. So I get, on the left-hand side, I get 1 plus 2 minus 7 plus 5, and that's what, 5 plus 2 is 7 minus 7, so this gives me 1. And on the right-hand side, I get 0 plus 0 plus c times 6 plus 0. So that tells me that c is equal to 1/6. All right, now let's see how do we get d, or anything else. So what I can choose is I can choose s is equal to minus 5. That's not going to be that pretty, so it's going to give me 125s plus 2 times 25, so that gives me 50, minus 7 times, minus 5, so that should be minus 125. So then minus 7 times negative 5, it's going to be plus 35, and then we're going to have plus 5 here. What is that? All right, so minus 125 plus 35 should get me minus 90, plus 50 gets me minus 40, plus 5. It gets me minus 35, I think. Did I do that right? Yes, I think that's right. Okay, let's keep going. So, choosing this to be minus 35, s equals negative 5. Let's see. Jeez, it's not going to be fun. All right, so we get 0, 0, 0 out of each of these terms, and the last term here is going to be the only one that's non-zero, so it's going to be d. Then we have minus 5 minus 6 cubed. And what is minus 6 cubed? Well, 6 squared is 36, and so 36 times 6 is going to be 6 times 36, 18, 19, 20, 21, 216? Yeah, all right. So we get minus 216. Okay, so then I get d is equal to 35 over 216, and nobody's happy. That's not a great number. Okay. 35 is 5 times 7, and 216 only have factors of 2 and 3, so they don't cancel at all. Alright, so that's not happy. Alright, so what do we do? Alright, so I have found so far C and D, but I haven't figured out B and A. So we're trying to figure out some good way of figuring out what these should be. There's a couple ways to go about this. One way that we can go about this is I can actually take a derivative of both sides. Another way to go about this is we just choose some random other number, and then we're left with an algebraic equation. I'm going to go up with a derivative of both sides for now, and we'll see how that works out. And that should give me at least one other term. So let's do it. So I get 3s squared plus 4s minus 7 is equal to, now I'm going to get a times some sort of triple product rule going on here. So I'm going to get an s minus 1 times s plus 5 plus, rather, we can just do regular product rule, right? So derivative of this times this plus the derivative of this times this, right? So it's going to be 2 times s minus 1 times s plus 5, and then I'm going to have plus s minus 1 squared. Okay? And I get plus a b times, looks like s minus 1 plus s minus 5, s plus 5. I get plus c, and I get plus 3d s minus 1 squared. Alright, we actually know c and d, so if we need them, we'll use them. Alright, but what I find now is if I plug in, say, s minus 1, this term cancels, but this one doesn't. So, s equals 1 again gives me this. Gives me 3 plus 4 minus 7, that is 0 on the left-hand side. And on the right-hand side, I get a times 0, and I get b, plus b, times 0 plus 6. So it gives me a 6 here, plus 1 6 as c, and plus 0. So that tells me that b itself is equal to minus 1 over 36. Alright, so now I'm trying to figure out whatever the heck a must be, and I can do the same game again. I'm really trying to get rid of this darned s minus 1 term out of here, so I can do something with it. Actually, no, this should be good, I can choose something else, and I can choose, say, s is equal to minus 5 now, and what does that could be? So on the left-hand side, I get 3 times 25. So that's going to be 75. And then that's minus 5 times 4, that's minus 20. And then it's minus 7. And so that's going to be 55 minus 7, so that's going to be 48. Is equal to, so now I get a times 2 times minus 5. Oh, wait, sorry, that whole term is 0 because of that guy. So I don't have to worry about that. So then I get negative 5 minus 1 squared, so that's negative 6 squared, and so that's 36. Plus b times negative 5 minus 1, that's negative 6. And I have plus c, and I have plus 3d negative 6 squared. Alright, so again, not looking pretty, but I do know all the other numbers. So I have 48 is equal to 36a plus, minus. B is 1 over 36, net minus 1 over 36. And so we're going to have a plus, and then it's going to be 1 over 6 here. C itself is 1 over 6 plus 3 times D, and D is 35 over 216. And this is times, say, 36. All right, so good news, a lot of these things actually simplify a lot. So we get 36a plus 2 over 6. That's nice. Now, 216 is 36 times 6. And then we have a 3 over here, so it's going to be 35 over 2. All right. So, let's see. Do I really want to keep working this out? I mean, I could just tell you guys, finish this up, go home, right? Anyway, so we get 36a plus, let's see, 2 over 6. And then I get plus 35 over 2, but if I want to make that over 6, it's going to be 105 over 6. Yeah. All right. And this should be equal to 48. Ah, boy. So let's keep going. Copy that. Go to the next page. Paste this. And all right, let's see what we got. All right, so ultimately that is 36a is equal to 48 minus 107 over 6. Oh my goodness. All right. So 48 times 6 is going to be just proving that I can do this, right? So 4 times 6 is going to give me 24. Plus 4, that's 6. No. That should be it, right? 24 plus 4 is 20. Yep. Okay, so that gives me 288 over 6 minus 107 over 6, and so that gives a 181 divided by 6. And then, so then A is equal to 181 divided by 6 times 36, which we already determined was 216. All right. Not all heroes wear capes. Okay, so we have A is equal to 181 over 216. B we got as negative 1 over 36. And we got C is equal to 1/6. And we got D is equal to 35 over 216. All right, now what did all this correspond to? It was corresponding to this, which was a Laplace transform of our equation, of our solution that we're trying to figure out what that solution is, right? So let's wrap this up. So A, B, C, and D, they're all gone. A is 181 over 216. B is minus 1 over 36. C is 1 over 6. And D is 35 over 216. So then that gives me a y of t. Let's go this one at a time. So 1 over s minus 1 inverts to being just e to the t. 1 over s minus 1 squared. Remember, 1 over s squared is equal to the Laplace transform of t. So that is just going to be, highlight. So we have minus 1 over 6 times t e to the t. Now the next one is a little slightly trickier. We have a 2 factorial over s minus 1 squared should be the Laplace transform of t squared e to the t, right? So what I'm going to do is I'm going to go ahead and I'm going to multiply and divide by 2. And so I get 1/2 out here times, then putting 2 back on top. That's just going to give me now t squared e to the t. And finally, plus 35 over 216 times e to the minus 5t. Okay, and there we go. This is the solution to our differential equation. Bit of a mess. I can clean up just a little bit and change that to 1/12. But that's the idea. Okay, so that's 2 examples straight from the book. And yeah, I think I'm gonna leave it at that one right now. Partly because my baby just woke up from the nap. And they're having a party. All right. Take care, and if you have any questions, if you aren't my student, then go ahead and put it in the comments. If you are my student, go ahead and post on Canvas, and we're going to cut back to my office.
Okay, so now we know how to solve some differential equations using the Laplace transform. It's not too bad, huh? I mean, all it really is comes down to taking Laplace transform for both sides. One side, you have to basically you get a polynomial. You have to worry about initial conditions here and there, but that's not too horrible. And then the whole thing turns into a rational function that uses partial fraction decomposition, and then you invert. So I hope everybody feels confident about using this method, and it really comes down to just practicing those properties of Laplace transform and also practicing partial fraction decomposition. That's mostly remedial for a lot of you because we did all that back in Calculus 2, but it's coming up again, and so be sure to go back and practice. Okay. All right. Well, thank you for watching, and good luck with your learning.